And I guess we should go ahead and start. We're a few minutes in. So I'm going to introduce all four of our speakers, and then we can get started. So Nick Brummell and Gustavo Guerrero are the leads for our Tachocline theme. They are mainly focused on the more theoretical and modeling side of the Tachocline, and Sarbani, Basu, and Sylvain Korzennik are both observers who do work down at depth near the Tachocline. Nick is a professor at UC Santa Cruz. He does research in the deep solar deep interior, examining fundamental MHD processes for dynamo theory, magnetic buoyancy instabilities, transport by convection via a mix of analytical methods and high performance simulations. Gustavo is a professor of the physics department at, and I'm going to butcher this entirely, Gustavo, but the Federal University of Mina, Gerais of Brazil. He's currently a visiting professor at NJIT, and he's mainly interested in the physical processes governing the solar magnetic cycle, which involve MHD, mean field dynamo theory, turbulence convection, magnetoconvection, and he's also one of the leads of the dynamo team. And Nick is one of the leads of the convection team. Sarbani is the William K. Landman Jr. Professor of Astronomy at Yale, and she specializes in the study of the sun and other stars using data from solar and stellar oscillations. And then Sylvain is at the Center for Astrophysics at the Harvard Smithsonian, and he's been studying the interior of the sun with helioseismic techniques for about 3 decades, kind of dates him a little bit. His research interests and expertise focus on mode fitting, time distance, and inverse methods, with a special interest in estimating both statistical and systematic errors associated with data analysis and inverse methodologies. So I believe that our observers are going first. So that's Sarbani and Sylvain, and they're going to catch us up on some of the the current observational status of the Tachocline. So Sarbani, take it away.
Thank you. Can you see the screen, the shared screen? So it's not just the current knowledge, observed knowledge of the Tachocline. It's more what we have been doing for the past 30-odd years, because we haven't really been doing anything new. So I'd like to walk you through what we do. So we all know that the whole Tachocline business started with the inversions for solar rotation. Not this one in particular, of course, because this is a new one, where you could see this sudden change in the rotation rate. Now, if we look at into a bit more detail, these are the latitudinal cuts. So here's the Tachocline, and here's the near surface shear layer, the 2 shear layers. Now, some of you attended a session on the shear layer last week, I believe. Today, we're going to talk about the Tachocline. Now, it was realized pretty early on that the resolution of these inversions is really not particularly good enough to figure out the Tachocline properties to the extent that we would like to, which is why most of the work in this field has been dealing with forward modeling. You assume a functional form of the Tachocline and find the parameters. So how do you parameterize it? Well, this is a rough schematic of the Tachocline. You have the jump in the rotation rate. This is actually the easiest quantity to determine. You have the position of the Tachocline, which is the midpoint between the rotation rate in the interior and the sort of when this becomes flattish. So somewhere here for the equator, somewhere here at 60 degrees. Let me see if I can get a pointer. Yes, somewhere here at 60 degrees. Then there is the width of the Tachocline, which is over what range is the rotation rate changing. And in terms of definitions, the position of the Tachocline, which is the center point, and the jump are reasonably well defined. The width, different people have used different definitions of the width. So we'll have to take a look. We have to keep that in mind. The whole game started with Sasha Kosovichev way back in 96, who looked at just one of the A coefficients, which is the A3 coefficient, which has the largest signal of the tachocline. He just did a simple least squares fit to a tachocline model, which is given here. And determined the properties R naught, which is the position, W, which is the width, and the amplitude. And this is the sort of result he got, which is this line here. Now, the way, given this functional form, the definition of the width is basically, it's the width over which the rotation rate transitions from 0.08 to 0.92 of delta omega. Okay, delta omega being the jump. So it's the full width of nearly the entire thing. Now, he plotted the same thing in the chi-squared space between the position and the width, and got a fairly nice result. So somewhere deeper than the base of the convection zone. Now remember, this is just one coefficient. Now I repeated the same thing with different data and a slightly different model of the tachocline. I used the fact that at deeper layers, below the tachocline, the rotation rate, at least with the inversions, it doesn't go completely flat, so there might be a trend. And the definition of the form was also different. In particular, W here, A, unlike Sasha, is the half width, and it's a change from 0.27 to 0.73 of the rate. So if the width is small enough, Sasha's width is 5 times my width. So just, if you want to compare numbers, that's to keep in mind. And around the same time, Paul Charbonneau did some work on this, again, using the A3 coefficient. And these show all the results. The solid and the dotted are mine and Paul's, and the dashed is Sasha's. And I wondered for a long time, why is Sasha's giving a slightly different result? At first, I thought maybe it's the definition, the functional form, but Paul uses the same functional form. Turns out it's this central thingy, adding a trend to the center. Paul's model had that. If you add that, then it doesn't matter which form, which model of the tachocline you use. This is different, and so these are MDI and HMI sets, trying to find the jump, the position, and the width. The circles are the model I've used. The small triangles within the circles are Sasha's model, and you can see that it's not the model that really made a difference. So once you add this term, things were fine. So there's a trend. There's a systematic trend that you need to take care of. Okay, those were just 1D with HC3. We tried 2D, where we put it in a latitudinal dependent. This was 98, a latitudinal dependence on the position as well as the width. We fit using simulated annealing because the simple least squares wouldn't converge. And we got a nice, the expected jump in the rotation rate. We also got a trend in the position and the width. Okay, now these dashed, the horizontal line here was the result obtained just from C3, if I remember correctly. So Paul Charbonneau et al., which included Thierry Corbin and Jan Christensen Dalsgaard, tried the same thing, a 2D model but the Tachocline model was Sasha's model. And they found that, yes, they could also fit a 2D model. And two, there is a latitude dependence of both the position and the thickness, and that the Tachocline is prolate. Now you have 4 sets of numbers here. It's just the first row that has the latitude dependence. The others don't. They did try inversions, but the resolution wasn't good enough, which is why these are the results they talked about. Okay. Since then, there hadn't really been much done. So Antje and I, way back in 2011, and again a couple of years ago, decided we'll just use what we had in our 98 paper, but with newer data, to look at the time dependence of the Tachocline. And we found a distinct change in the jump with time. So this is the equator. The gray in the background is the sunspot number. So you can see that cycle 23 and 24 do not look alike, and which is much more dramatic if you plot the jump as a function of the 10.7 centimeter flux, because cycle 23, which is the red and brown, and cycle 24, which is the blue and purple, they have different results at the same value of the surface activity. I haven't looked at the available cycle 25 data. What I'm hoping to see, of course, a few more sets of data will confirm it, if the Tachocline actually follows the 22-year cycle rather than the 11-year cycle. It clearly doesn't follow the 11-year cycle at the lower latitudes. Now, systematic errors. I mean, this whole team is to look at, get definitive answers about the Tachocline. And the problem is, if you use GONG data, red, versus HMI or MDI, which is blue, or HMI, which is in cyan, you get a slightly different answer, as you can see here. So this is each circle, each point is a data set. And I've just used C3 here to show this. So you can see things are good. There are systematic errors between GONG and MDI and HMI, which we really need to pin down before we can say things are, exactly what the Tachocline is like. There are more systematics, this is from the Antje and Basu 2011 paper. It's just showing that the GONG, at that time we didn't have HMI, so GONG and MDI data have different results. So these were the results of forward modeling. I'm going to hand over to Sylvain, I believe now, to talk about the problems getting Tachocline and what we need to do before we can get Tachocline results from rotation inversion. Sylvain, and just let me know when you want me to change the.
Thank you, Sarbani. So, apologies for those who actually have seen, presentation about inversions, but I want to just remind everybody, the problem of the rotation inversion, which is a linear problem, and to a pretty, good accuracy, we know what the rotation kernels are. The problem is that, the problem we're trying to solve is intrinsically singular, which is another way of saying that we need to divide by 0. In practice, we have to divide by very small, quantities. So we divide by, what should have been, their epsilon, which is mean that we have noise magnification. So there is always a problem that we need to live the singularity and choose a trade-off between noise magnification and spatial resolution. And we have actually a way to measure the spatial resolution, which is the averaging kernel. So in some way, we know how well we resolve, the solution that we compute. And essentially, the second equation shows that the estimate of the solution, it's essentially a convolution of the true solution by some, averaging kernel. And there's been a lot of discussion, about details, whether we should use expansion coefficient, and for many of those, and some of us have been arguing that you effectively do some pre-smoothing of the solution because you limit already your data set to an expansion. The other approach is to use directly frequency splittings, and therefore we have a larger data set, and there are issues about rejecting outliers because in practice, U-fitting is never very good. And those details really matter when we look for small effect. Sarbani, thank you. Next slide. So I'm going to show some, rotation inversion that are really from a simulated data set. This is part of the, initiative that Mike Thompson started about, having a lot of inverter to compare their techniques. There is a forward calculation, which essentially Sasha made up some profile. The range of modes that we invert match actual observation. And actually, even though when we invert noiseless data, we associate to those data an error bar that corresponds to realistic uncertainties, even though we use a quite long time series. This is a 6.3 year long time series. We also have, noisy data where we can add random noise, which means we don't add systematic noise, but random noise. And we know that there are no systematic errors, so essentially we know that, or noise at the numerical level, very small. So I'll show you, some solutions using a regular least square that, Antonio Darwich and I have done. And while the solution are computed in a regular target grid, you'll see that the solution are remapped on the effective grid. Next slide, please, which is really the center of gravity of the averaging kernel. Sarbani, next slide, please. So in the upper left is the model that Sasha came up with, and people may recognize some feature that have been claimed to be seen, I highlighted to jet, a very, narrow tachocline, some oddities happening around the tachocline, and of course, the rotation constant, in this case on cylinder. The upper right is actually a solution using noiseless data with a very low trade-off coefficient. So the data are smoothed as little as possible. And if you look carefully close to the surface, there's some wiggles that we know are not quite real. You can see that you recover most of the feature. The lower left is actually the difference between the model and the solution. And except where there is large gradients, we are well within a nanohertz. This is, of course, noiseless. You also can see that we cannot recover the solution, closer to the center and closer to the rotation axis, where essentially the averaging kernel are not well localized. Next slide, Sarbani. And those are, again, solution where I just simply increase the smoothing and still use noiseless data. And if we go to and essentially what you can see is, obviously, as you increase the smoothness, which is because you increase the trade-off to reduce the noise magnification, you smooth out the solution, you lose the details, but you can see some of the feature, and you also lose localized averaging kernel where the solution is not well constrained, which is closer to the center and the rotation axis. Next slide, please. And this is actually the noisy data. So of course, this is random noise of the simulated data, so there's no systematic there. And you can see for the same 4 trade-off that you do want to have a pretty high smoothing if you want to get rid of what is obviously, wiggles due to the noise. And you can see that actually if you compare, if we go back to the previous one and back to this one, and you look at the lower right, the next one, and next one, the one in the lower right is very similar, whether you have noise or not. So you can essentially say that with that trade-off, the noise doesn't really matter. The fact that we've added the noise, random noise equivalent to 6.3 years of data. But obviously we've lost a lot of the resolution of the details. Next slide, please. So the way to think about it is that there is always what I call the spatial-temporal trade-off of heliosysmology. We can always try to use a longer time series to reduce, to improve the precision, reduce the uncertainty. But if we're looking for a signal that change with time, we'll essentially average it out. You also have to be very careful when you look at changes of the value, because of course you can decide to have less of a trade-off to try to detect sharper feature. But in fact, as a function of time, the precision or essentially activity change the signal to noise ratio of the observation, where the noise is not really incremental noise, but it's of course solar noise. So we have often fewer modes and larger error bars when there is higher activity. And if you invert the data at the same trade-off value, you will end up having wider averaging kernels. So you can have the impression of seeing a change with time, when in fact you have a change of resolution because of the distribution of the noise in the data. And this is about, sort of random errors. On top of that, we know that we have systematic errors. Sarbani showed you earlier, and I think there'll be another plot, where essentially if we use different fitting techniques or different data, we don't come with the same result. This being said, we've really improved very much the inversion techniques, and we've reached a point where people really want to compare and well understand how well we can invert data and what we can trust in the inversion. And there is, I think, still room to improve both the mode fitting and the inversion methodology, because we can target the inversion. For instance, we can try to target inversion to have the highest possible resolution at the base of the convection zone or around the Tachocline, and not care about what's happening near the surface. Thank you, Sarbani. Next one. You want to take over this one, Sarbani?
This is just a compilation of a lot of the published values for the position, both as a function of time and latitude, and the width. What has not been done in this figure is the conversion for the width. So take the width with a grain of salt, because you'll have to multiply all the Antia and Basu results by a factor of 5 to compare with Charbonneau and Corbett. Now the Wilson et al., I don't remember what their definition was, unfortunately. But yes, so you can see the Tachocline is thin. These are all, incidentally, most of these at least, are all forward modeling results. But there's a lot of work to be done yet. In terms of time variation, if all you're interested in is how does the change look like in time, I would say stick to one instrument. And then, because at least the time variation is, the shape of the time variation comes out to be the same, whether I use GONG or a combination of HMI and MDI, but there is this systematic difference between them. And the thing is, the systematic difference is not just at the base of the Tachocline. I missed the near surface meeting last week, but even in the near surface layer, whether you use GONG or MDI plus HMI, you get a difference. So that is an issue. Otherwise, I think this is basically the end of our talk, which, sorry if this sounds a bit facetious, but we know there's a Tachocline. We know roughly the properties of the Tachocline. I think we're fairly confident that the Tachocline is thin, that there's a jump which is latitudinal dependent, and also that the position is latitude dependent. But if you ask me to bet my salary, forget life, salary on what exactly is the position, I would not do it, because GONG and MDI or HMI would give me 3 different numbers. So that is an issue right now. So Thanks.
And Sarbani, if I can add one more comment, is that, you know, a lot of work has been done in forward modeling, but you want to remember, you know, what the inversion tells us. And if the inversion tells us that we have a wide averaging kernel, in some way it says that in the forward modeling, you have a very low constraint of some of the parameters. So yes, you know, you run, you know, some annealing, you run some, you know, least square. In the forward model, you get a value, but you have to remember, you have to be cautious about what is the precision of that value and how quickly that value can change by a substantial amount, especially as a function of time or data set, because it is poorly constrained. The inversion tells us, you know, where we have large or wide averaging kernels, where we know that it's very difficult to get a focus and a very clear measurement. Thank you.
Indeed, that is correct. But this is where your earlier comment that you can focus the inversions to the Tachocline. And that's basically what the forward modeling is doing. Forget about the very close to the surface, forget about the core, focus just on the Tachocline. Do a proper, try to get the probability distribution instead of just a number and an error bar, so that you know exactly what the widths are.
Yeah. So Nick and Gustavo, I'm going to kind of let you decide. Do we want to take a couple questions on the observations now, or do you want to move on and we can return to questions at the end?
Let's take a couple of quick ones if somebody wants to desperately ask something.
There's a couple questions in the chat. So Todd is asking, what do we need to reduce the systematic errors?
Let me try and answer that. I'm sure Sylvain has a different answer. One is to understand what the origin is. I know for a long time there was this issue about a 2 nanohertz difference between GONG and MDI splittings that turned out to be because of, correct me somebody, sidereal versus synodic issues. So we need to be sure that we are comparing like with like. And also, what are the modes where things are causing the differences? Like with MDI, we've consistently found that modes of L greater than 120 cause issues. We don't know why, we haven't quite looked into that, but they do. So that's there. And so we need to figure out which modes are causing the issue, and then perhaps people who actually fit the modes, like Sylvain or Jesper, can comment on the other part.
Sylvain, do you have additional
Well,
comments?
you know, the problem has been that, you know, for quite a while, there've been very few people interested to improve the fitting and looking at the different way of fitting the data. And we've reached a point where if we want to make sure that we can measure small effects, we need to start by looking at the input data set and how well it is fitted. You know, I've done some fitting, even changing, you know, the leakage. There are a lot of boring things and complicated things about fitting the data. But when you change things and you compare, you fit the same data slightly differently. Some of the difference are not simply, you know, add the noise that you would expect. So you know that we have not a perfect model in the fitting. And if you want, and essentially it has become a subject that was considered, it's all solved, we know how to do it. And I think that this needs to be sort of reopened. You know, I've talked, you know, I'm not seeing Sasha, but Sasha in the past I've been saying, I look at, you know, the JSOC data and they're systematic, Sylvain, you know, give me your data, which actually I did. We need to look carefully. You know, I'm the last one will say that my fitting is so much better than Jesper. You know, first, I don't want to get into a fight with Jesper because he's a friend, but the point is not to say that one is better, that if you do it differently and you don't get the same answer, you know that you're doing something wrong. And so where there is, I think there's plenty of room for improvement. It's not an easy job. And we know that when we compare even, you know, MDI and HMI over the same, you know, time when we use the same epoch, you know, when MDI and HMI looked at the sun at the same time, we see differences that are not at the level of the estimated noise. So either our noise estimating is wrong, or most likely there is some other systematic there that comes in. So that's a difficult problem. But if we want to make progress, we need to do. And one of the things is that this collaboration is a source of motivation to get back and revisit and say, no, can we do better than turning the same crank we've been turning for 20 years?
I think we're going to move on to the more theoretical side of things. Brad, I see your question, but we'll circle back to it at the end.
Okay, can everyone see everything and hear everything? Are we good?
Yep.
Okay, can I get this out of the way? Yeah, there we go. All right, so we're just going to talk a little bit about the theory, and this is something that Gustavo and I sort of threw together. So, and we don't have an awful lot of time, so we're going to skip an awful lot of details, but hopefully a bunch of you know what's going on. And for those of you who don't have any idea at all, like some of the class of ours that have showed up here to watch, sorry, I'll try and do my best to give you enough of insight to understand things. Oops, let's move. There we go. We keep talking about the tachocline as being thin, but thin in what sense do we mean thin? Well, what we really mean is thin in the sense of if we think about what the dynamics that we might expect to be going on, then it should be thicker. So something is stopping it from being as thick as we might expect. And what are those processes that we might expect? Well, the first thing you could think of is just purely viscous spreading of the tachocline. If you just took the purely microscopic viscosity and the age of the sun, then things should have spread by about 5% of the radius, which is about in agreement with the thickness of the tachocline. Maybe things are a little thinner than that by most estimates these days, but it's about that. But this is an absolute lower bound, and if there was any turbulence, and so there was any higher effective viscosity, then you would expect more spreading even from viscosity, purely viscosity. So that's one thing. And if you don't like that, then there's a second sense, and that's this idea of radiative spreading, which is an idea which has been around for quite a long time in the sense of spinning down stars. But it basically goes like this: in a fast rotating thing, where the Coriolis force sort of dominates pretty much everything else. Then if you apply some sort of torque and get a differential rotation, then this differential rotation tends to propagate, spin up, via secondary meridional circulations. And you're all used to this because this is like Ekman pumping in your teacup. Here, you've induced fast rotation in the bulk of the tea, but the frictional forces at the bottom cause a differential rotation at the bottom, and then unbalanced pressure forces drive this meridional circulation. That's in an unstratified case. If you make this stratified, turned it upside down, now the tea is falling out of my cup because I'm spinning the top. Then what does stratification do to this? Well, the same sort of thing happens to start with. We tend to spin things up, adiabatically to start with. This is sort of teacup style burrowing or spreading of the differential rotation of the lid. This is when the rotation can overpower the stratification and then force the Taylor-Proudman constraint to a certain depth. But then, the stratification senses the stratification, and to overcome that, it has to use thermal diffusivity to relax this constraint, essentially. But you still have an imbalance of pressure forces, which gives you thermal gradients, which drives a meridional flow, and then angular momentum gets transported in the same sort of ideas as you had before. And Spiegel and Zahn did a great job of just describing this nicely. This equation down here is the evolution of this differential rotation, the propagation of this differential rotation. And you can see it has two terms, one of which is just the viscous spreading, and the other is this hyperviscous term. So it's a d4 rather than a d squared, so it's hyperviscous. And it has some coefficient which is related to this time scale, which is this slow Eddington-Sweet time scale, which involves the stratification, the rotation, and the thermal diffusion. So if you apply this to the tachocline or to the sun, then over the age of the sun, any flows, any differential rotation should imprint about 40% of the radius. So again, the tachocline should be much thicker than we're observing. And so when we say thin, that's what we mean by thin. So the conclusion is that standard angular momentum transporters should have thickened the tachocline beyond what is observed. And so you need something to prevent this from happening. So you need another source of torque, force, stress, whatever you want to call it, to alter the dynamical balances in these things and to counter the radial spreading and to homogenize the latitudinal, the variation of the differential rotation. There's two main categories of the way people do this. One is purely hydrodynamic and the other one uses magnetic fields. And I'm going to talk a little bit about both of these right now. In the purely hydrodynamic ones, the majority of people think about the first one of these, which is that, you know, anisotropic turbulent diffusion in the strong stratification. And I'll say exactly what I mean by that in a second on the next page. But there's also been another idea, which is purely hydrodynamic, and that's dissipation of different directionally traveling waves. And I'm only really going to talk about the first one because the second one was sort of dismissed for some of the same reasons as the first one was queried. So let's just talk about that one to start with. So in the purely hydrodynamic tachocline, this is an idea, the ideas of Spiegel and Son, again, carrying on from what they did before. They wanted to isotropize or homogenize the interior, and they said that seeing as everything is very, very strongly stratified down there, maybe the turbulence down there is two-dimensional. And if it's two-dimensional, then the turbulent diffusivities you get out of these things may be very different in the horizontal direction from the vertical direction. And things may tend to much more strongly homogenize in the horizontal direction. So I get this anisotropic turbulent diffusion, which homogenizes things in latitude rather than in the vertical. So this is the idea that the turbulence down there acts as sort of like a horizontal friction, which homogenizes everything. And this is what a lot of people call the fast hydrodynamic tachocline. What are some things we have to think about with this? Well, first of all, is there turbulence in the tachocline? Is there any instabilities in the tachocline which lead to serious turbulence down there, as opposed to just residual turbulence from above? And lots of people have worked on ideas for what may cause the tachocline to be unstable, because it's not completely obvious to start with. You know, if you do a very, very initial first glance, it looks sort of marginally stable. And so you need to go, you know, to a little bit more complicated dynamics to try and get some instability in the turbulence. So maybe it needs to be a nonlinear instability. Jean-Paul Son himself and Denis Richard did some experiments to try and show nonlinear instabilities. And then there's been all kinds of a zoology of MHD instabilities that Peter Gilman and Mausumi Dipati has championed. More recently, Pascal Guerrero has been looking at stratified shear in low Peclet number situations to try and see what happens there too. Even if there is turbulence down there, if it exists, is this turbulence necessarily quasi 2D? And Pascal has been doing, like I said, just been doing lots of interesting work on this. And my impression of her work so far, and you should get her to give us a seminar on it, which will be much more complete and much more informed. But my impression of it was that it's not obvious that things are very, very two-dimensional when you take into account the full stratification situation and low Peclet number at least. So interesting work moving on that front. Even if this turbulence was quasi 2D, does it actually act to transport angular momentum towards a state of, you know, homogenization? In other words, does it really act as a friction? There was a big query about this raised by Goff and McIntyre in 1998, around that sort of time, by saying that in analogy with atmospheric models and other models, fast rotating two-dimensional turbulent situations tend to form jets. I mean, look at Jupiter. So usually there's an inverse cascade towards large scales and mixing of PV, and that tends to form jets. So this is the opposite of homogenization, right? So all of a sudden there was this query which said, in 2D constrained or rotating turbulence, does things act like a friction, which is what Spiegel and Son said, in other words, homogenization, or does it tend to anti-homogenize or act as an anti-friction, which is Goff and McIntyre and other people were saying. And some people have done a bunch of work on this, you know, to try and figure out by actual simulations whether this is true, Mark Misch, and the conclusions are very scattered and somewhat inconclusive, unfortunately. Sometimes you get latitudinal friction, but radial anti-friction. Pat Diamond in 2011-12 with some coworkers said maybe it's scale dependent. And then Steve Tobias, again with Pat Diamond, Dave Hughes, came along and said, well, if you throw a little bit of magnetic field in this, you can completely 2D rotating sort of beta plane, jet forming stuff, if you put a bit of magnetic fields in it, you can destroy the anti-friction. So, I mean, my conclusion of this sort of stuff is there's a lot of stuff here which is still very, very unresolved. And so there's plenty of space to move forward with some of this stuff. The other option is to use magnetic fields to provide the magnetic stresses, which try and counter the radiative spreading. And there's two main categories of proposed fields. I think actually you put on here, there's possibly a third one. But the two main categories that people talk about are having a fossil magnetic field in the interior and a dynamo magnetic field in the convection zone. But there is this third possibility of maybe there's some other weird things which are strengthening magnetic fields in the tachocline itself via MHD instabilities and turbulence, which hasn't been considered quite so much. Mausumi and Peter, again, sort of the champions of a lot of this sort of stuff. And this is a third possibility. But looking at the first two possibilities, I mean, one thing to note up front, what's the benefit of magnetic models? If there's no magnetic field about and I'm rotating quickly, purely hydrodynamically, then there's the Taylor-Proudman constraint, and you tend to imprint things on cylinders, in other words, parallel to the rotation axis. If there's magnetic field around, then differential rotation propagates along field lines. This is Ferraro's law. You know, in other words, field lines are strong constraints. It's hard to bend field lines. So shear tends to get homogenized so that the differential rotation propagates along the field line. So this is a good source of homogenization, magnetic field. So in the first scenario, fossil field scenario, McGregor and Charbonneau were the sort of first to suggest that if all the fossil field lines in the interior of the sun were actually confined to the radiative interior, then this is a nice way of homogenizing the whole of the radiative interior. And that is what we see from helioseismologies. The radiative interior tends to spin as a solid body. So if the tachocline was largely large-scale field free, then there wouldn't be an awfully strong coupling between the differentially rotating convection zone and the interior. So if there was a sort of a buffer zone between the differential rotation of the convection zone and the deeper interior, then you can have the deeper interior sort of rotating as a solid body. So it sort of changed the way we look at the problem to one of magnetic confinement a little bit. How do I keep all of the field lines sort of confined to the interior so that things get homogenized in the interior? That's a confinement problem. And there's sort of two ways of doing this. This is where, whoa, sorry, I went to the wrong place. Goff and McIntyre says, well, you have this burrowing thing, so why not just use the meridional flow of the burrowing mechanism of this radiative spreading mechanism to balance the outward diffusion of this field. And so the time scale of operation of that then is this meridional circulation time, which is related to the Eddington-Sweets time, which is very, very long. And they actually estimated that the ventilation time of the tachocline was about 1 million years. So this is a slow process. And so people have come to know this as the slow magnetic tachocline. There is another way you can confine things. There's the gamma effect, which says that turbulence tends to transport large-scale magnetic field against gravity, or down a gradient of turbulent intensity, which in this case is from convection zone out of convection zone, which is below the convection zone, so that's downwards. And this is a different time scale for confinement. This is a turbulent time scale that does this. You transport on the turbulent turnover time scales. So this is also fast. This is also fast in the turbulent cell. So you could call this a fast magnetic time scale if this was the thing that did the confining. Now, maybe we need both of these because this fast magnetic confinement doesn't work so well at the poles where magnetic field tends to be more vertical. The slow magnetic confinement can do this, so maybe we need a combination of both of these things for this situation to work. This is the slow and the fast magnetic time scale. One which has come to the fore a little bit more recently, and for reasons I'll say in a second, is instead of using a fossil magnetic field to provide the magnetic stresses which counter the spreading, use the dynamo magnetic field itself. So this is a sort of top-down stress inducing as opposed to bottom-up stress inducing, if you want to think of it that way. This was put forward by Forgas Dijker and Petrove in 2001, who said, essentially, if I have an oscillating dynamo field in the convection zone, then that penetrates a certain depth, a skin depth. Any oscillating field does this. We know this from undergraduate physics, and that skin depth is related to the diffusion, which in this case we would assume would be turbulent diffusion, and the oscillating frequency, so which we know is sort of 22 years or whatever. And so their idea was that this thing would provide the stresses, and clearly this has a different timescale. This has the dynamo timescale, the oscillation of the dynamo cycle timescale. So this is fast compared to the slow one, but not fast as the turbulent one. So this is maybe the fast-ish magnetic times tachocline. There's a question of what balances, what are the major balances then in the actual tachocline itself. If I have this penetrating, if I have some Maxwell stresses from this penetrating field, what are they balanced? Some say it may be turbulent viscosity, and then alternatively, it could be balancing the radiative spreading itself. So what actually happens, which of these balances is dominant is an interesting question, which has been somewhat explored, but not tremendously explored yet, as I will say. But in general, this idea of the dynamo magnetic field being the thing that provides the stresses has been examined quite a lot recently, because if you just did a dynamo simulation and left room for a tachocline, in other words, had a convectively stable region below your convectively stable region in your model, essentially you are running this scenario and you can see results from it without trying too hard. Well, sorry, trying too hard. Yeah, you have to do millions of computer hours or whatever, but it'll happen for you fairly naturally. So the work in this area, you know, there's two things have sort of come about. There's been an extension of the original model. There's a really nice paper by Barnabé, Antoine Strugener, Paul Charbonneau, Sacha Brun, and this was the last thing that Jean-Paul Zahn does it. So we all have a lot of empathy for this great paper. And essentially, what Barnabé and Strugener and the gang did was to extend the original model, slightly different boundary conditions, confirm the earlier results, and then also did, you know, the balance in that original model. The dominant balance is this fast-ish balance in the tachocline. In other words, the dynamo, which is the fast-ish, the dynamo Maxwell stresses are balancing turbulent, you know, Reynolds stresses essentially. So that's the dominant balance there. But they also extended, Barnabé et al. Also extended it so that it balanced the radiative spreading. Now, these are 1D models. What do you get out of the 1D models? You essentially get an idea of what parameters can allow these balances to cause a thin tachocline. So you get pairs of, well, pairs, you get groups of turbulent diffusivities and timescales, etc., which will work to give you the balance you want. So it's not conclusive, but it tells you under what circumstances, you know, how much turbulent diffusion you do need for this to actually work, for example. Now, there's been some 3D simulations of this sort of stuff. There's the Millennium simulation that Dario Passos and Paul Charbonneau and the gang did. Oh, actually, not the gang, I guess it's just them. Gustavo's done some work on this, where you have tachoclines below a dynamo model. And I just want to highlight this one more recently. Lauren Matilski and Yuri Turme, both of whom I think I saw here. So hi guys. There's a Cambridge Cool Stars paper out which describes some of these things, and I just want to highlight this. Although Lauren just gave his thesis defense, passed with flying colors, and is going to come and work with us at COFFIES, so that's awesome. And hopefully the paper on this stuff with more details will be published soon. But I just want to tell you this result they have from their simulations, which I still stole from the Cool Stars paper. Essentially, they ran a dynamo like this with space for a tachocline, did a purely hydrodynamic case, and then did an MHD case, which had a dynamo running, and ran for lots and lots of cycle times, etc. And you can see this is the differential rotation essentially plotted here, and you can see the big difference between the hydrodynamic case and the MHD case. In the hydrodynamic case, you get whatever differential rotation propagating into the interior. In the MHD case, the tachocline is pretty much homogenized and evacuated. So you would say, whoopee, we're done, right? Except, well, what are the exact balances in here? I think the balances in here are these Maxwell stresses balancing, in their case, actual viscosity, which is higher than it should be for a real solar simulation, of course. So everyone, this is what everyone does. You know, no shade thrown here. It's just, you then say my higher viscosity is actually trying to represent turbulent viscosity, and the balance here should be between these Maxwell stresses and Reynolds stresses essentially here. So it's interesting to wonder what will happen as the viscosity went to 0 in this actual problem. You know, can we get the actual Reynolds stresses correct in this thing? So anyway, and what happens deeper down? I think Lauren has some very interesting results. We show sort of Rossby-like waves down here, which homogenize the deeper. How do things imprint downwards when this sort of top-down scenario is a very interesting problem? Great work. Look forward to having Lauren come and hang out with me and us, the gang in UC Santa Cruz and the COFFIES gang. Anyway, I think this is the stuff I already said, so I can skip that. And these are the issues that I already said, so I can skip this sort of stuff. The thing is, now we have this sort of zoology of models from, you know, hydrodynamic models, and we have magnetic models, and there's slow, and there's fast, turbulent, fast, and there's fast-ish, which are not as fast as turbulent, but are dynamo timescales. And we have subversions of these models depending on, you know, what do the actual confinement in the slow models and what the actual balances are against in the fast models. And all this, I started writing this talk and sort of ended up with, you know, fast, 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 slow, fast, fast-ish, and it starts getting a bit confusing. I suggest that maybe we reassign some names here, might be a better way of doing things, but let's not worry about that too much for now. All of these models have pros and cons, some of which I've already mentioned. In the hydrodynamic one, where do the instabilities come from? Friction versus anti-friction. The confinement models, whoa, is this slow process? I mean, it seems so, you know, it's so slow. How can it be any use to any of us? What is the role of turbulence compared to these slow processes? Maybe we need both turbulence and slow processes to operate at the same time for this to work. And then the dynamo ones, this you would really need to understand turbulent diffusivities in the tachocline to know whether this is going to work. And of course, almost all of those things are very, very difficult things to do with simulations. To combine slow and fast processes is very, very difficult. To understand turbulent diffusivities at the sort of levels of turbulence you might see in the sun, very, very difficult. So these are, this is what's going to keep us busy for the next few years. Whether it's the slow version or the fast version may come down to whether these are layers of the tachocline. We know there's convection zone, we know there's an overshoot zone. Those are probably the same in both situations. So we know there's a deeper rated interior. It's what happens between may determine what's going on here. For the slow version, we sort of need this field-free-ish buffer zone between the two things. So can we keep a sort of field-free zone to let this version work? Or in the fast one, you know, now we're saying something different. Now we need this oscillating magnetic field to penetrate a skin depth through most of the tachocline. So this is a sort of a weak MHD, possibly MHD turbulence filled zone, which is different from the other scenario. Which of these two it is, at the moment we have no idea. So that's COFFIES for us. That's what we need to do. We need to take the next few years to try and figure all this stuff out, right? That's what we said we're going to try. Obviously, the models we can compare and contrast and try and combine them and try and compete them against each other. But that type of stuff are very, very difficult if you want to do them simulations. It's very, very hard to have a model where you can have turbulent diffusion done accurately and well represented and slow rotational effects at the same time, for example. Very difficult. Certainly can't do it in a solar parameter regime, but can you find a parameter regime where the timescales are in the right order, even if they're not the right distance apart, is a big key to doing that. And of course, you know, we need to collaborate with the first half of this talk with the observations and try and come up with some really, really good ways of discriminating between these theories. So timescales is an obvious thing to look at. So timescales of variation of things in the tachocline, it could lead us a long way to sort of understanding some, because these things operate on very different timescales, although some of them cross over and emerge and are difficult to say whether it's going to be only one of these mechanisms and not some combination of these mechanisms, that make this hard. Latitudinal variation of the thickness appears in some of these models and not in others of the models. That might be a good discriminator to start looking at as well. Thermodynamics, if we could understand latitudinal temperature differences, whether thermal wind balance was happening deeper down, this sort of stuff would do too. So I think this is our goal for COFFIES, is to think a lot more about this last slide and try and come up with some things which are very, very discriminatory, both in the modeling sense and in the combination with observation sense. And that's it for me. I can't hear anybody. Is anybody out there?
Gustavo, do you have anything to add before we
No.
start taking questions?
No. It was very nice. Thank you, Nick.
So I know that we're at the top of our hour, so I want to, before we get to questions in the chat, make sure that anyone who has questions that has to leave has an opportunity. Does anybody have a pressing question that they want to ask before they have to go? Okay, hearing none, I guess we can go back to some of the questions in the chat. And I was going to go through them in order of when they were asked. So Brad, we can return back to your question. I don't know if you just want to speak up and ask it directly, or. Maybe he already left.
Brad here.
Yeah, he might have already dropped off. Brad's question was directed to you, Sylvain. Do the inversions provide any evidence for latitudinal variation in the position or width of the tachocline?
Well, Sarbani can correct me, but I think it's a little too early. In principle, we hope to be able to do it. The problem is really, it's twofold. If it's constant in time, then we can try to use the longest possible time series, and therefore we'll get a better precision. But if it changes with time, then it becomes difficult, because as you use a shorter time series, we'll probably have wide averaging kernel. And if memory serves me right, Sarbani correct me, I think the width of the averaging kernel increases with latitude, because as we go closer to the pole, it's harder and harder to get. So you have to be very careful. There's observational, you can say, well, the estimate of the width increase with latitude, but if it's due to the fact that essentially the width is a convolution of the averaging kernel width by the intrinsic width, then we make fuller cell, which is why you have to be very careful and look carefully at the averaging kernels and how they essentially blur or convolve, the inferences. Sarbani?
No, I agree. I mean, if you just look at the beautifully colored color maps, yes, it does look like it's that the tachocline becomes wider at the high latitudes. But again, the question would be, is that because the averaging kernels are wider? And one thing people haven't done, which can be done with at least one of the inversion techniques, solar, is just try and keep the same averaging kernel width. But in that case, of course, the compromise would be in the errors. So I don't think anybody's really bothered to do that.
Yeah, that's essentially the problem, Sarbani, is you can essentially, there are plenty of trick. It doesn't need to be solar, but you can say, yeah, let's try to keep the averaging kernel the same, but then your error magnification will shoot up. And remember, our data have systematic errors. So if it was only strictly, statistical noise, you can say, well, there is a trend, there is not a trend, even though it's poorly constrained. But if on top of that, we have systematics, and some of the systematics have to do with change in latitude. The expansion in coefficient or not is essentially a pre-smoothing as a function of latitude, if you want to look at it that way. So there have been a lot of argument, and I've spent a lot of time arguing with my dear friend Jesper, whether one way or another, is essentially injecting, some preconceived opinions on the solution.
Yuri, do you want to ask a question?
Well, I have a basic question of, we have a great deal of helioseismic data. There have been some attempts to work reanalyzing them or to test the sensitivities to reanalysis, something that Mike Thompson was also seeking to encourage. But are there actually the resources to do that? It's nice that COFFIES has an emphasis on the theoretical part, bringing these things in, but at least in our country, one gets a sense that these aspects of the subject, we are collecting data, but there really aren't the resources to systematically rework things. And in some ways, Sylvain mentioned that, so did Sarbani, but any comments on this?
Yes, it's a pity, that it's not being done. So I know Jesper and Tim Larsen did do a sort of reanalysis of the MDI data, and you can see the differences in the old and the new data. The new seem to have fewer funny features, but that doesn't mean it's free from funny features. And the basic problem in my mind is basically it's Sylvain who's doing the fitting, and then it's Jesper and Tim, that combination, and there's absolutely no one else who's looking into this problem.
And Yuri, if I can jump in, it is indeed, and you've heard me say that before. I said you spend so much money into building the instrument we're operating, and it gets very difficult to get the money and to motivate, a younger person to say, I'm going to try to rewrite the fitting from scratch, because what we've done, is improve methods that we've wrote 20, 30 years ago, even though my method is a bit more recent. And the question, as you said, has been, how do we get? And what I'm trying to flip is to say, if COFFIE needs that, this is how, COFFIE has this collaboration can say, we need to find some young Yahoo that is willing to tackle a difficult problem. Because, we're 90% there, but you want us to be the 99% there. And those last 9% is a lot of work to get it right. And so it has been kind of difficult. We had discussion about, proposal about global geoseismology don't get funded because a lot of people see it's a solved problem. And a few of us have been saying it's not a solved problem, because if we want to answer some of the questions asked today, we need to really look carefully. People are, analyzing dog data, which is a fitting method that was written 35 years ago. And we know the long list of things that are done wrong, yet people are still analyzing those data. Those tables. Sorry, I interrupted you.
No, I was just saying it's not a sexy problem, which is why neither NSF nor NASA like to fund, people to actually do the job. So if there's room within COFFIES to actually look at it, that's what needs to be done. I see, I'm a user of the data, and as a user, to me, it's a bit frustrating when you uncover these differences and there really isn't much I can do, but at least I can uncover the differences, which might be the first step to solving them.
Maybe Phil has something to say about this.
Yes, it's not true that there's no other group working on this. Ed Rhodes and Johan Reiter are quite busy with Johan's newest model for fitting, and they have some very interesting looking results coming fairly shortly.
Okay.
So, yeah. So
yeah, no, I should have remembered Ed and Johan, except since they don't. I've been hearing that they're going to publish frequencies for so long. I suppose they slipped them up.
This is a problem.
But still, aren't they focusing on high degree and not intermediate degree modes?
Sorry, right now the current tool goes from L of 1 all the way up to L of 1300, and it matches Birmingham and it matches Jesper. So. But they've been doing a lot of work on where the noise is. So it just keep your ears and eyes open. It'll come along in a month or so.
Kieran, do you want to ask your question?
Yeah, my question is along the same lines. It is more or less a suggestion. Because Sarbani has showed there are differences between gong and MDI, and why can't we think using same fitting method for two different instruments, and then we will know whether there is a problem with the mode fitting using different methods or it is because of the observations. So I think this kind of work was done long back for the solar
2003.
rotation.
No, also for structure.
For the, yeah.
It was done 2003. There were two papers, one after the other.
Yes. So for the Tachocline also, we can think doing the same thing with same method, or right now actually we have three different pipelines. I will not say pipeline. There are three different methods for mode fitting. One is Sylvain's method, other is Stanford, and third one is gong. So we should try to ingest data from MDI or HMI to gong pipeline, and then same thing for the gong data into the HMI pipeline, and see how much differences we get. And if there are differences, so we know like this is nothing to do with the fitting, it is basically the observation, because we are looking at too many different factors when we try to compare our results.
But Kiran, you cannot quite dissociate, because essentially you have a different leakage matrix when you put the different instruments. So you can always try to, Jesper has pushed some gong data, but you have to compute a different leakage matrix. And if or error is that the leakage matrix is not computed well enough, for both cases, then you don't know what you're getting. We know that even when MDI and HMI have observed at the same time, the frequency produced have differences that are not, of the size of what is the uncertainty. They're larger than what the uncertainty said the difference should be. So we know that the same method on slightly two different data sets taken at the same time give us, some systematic differences.
I do want to point out this is related to a question that Todd asked in the chat about would observations from a different vantage point be critical as well, such as solar orbiter? And Sylvain, you kind of answered that in the same sort of way, but just it's a related question.
So for global helioseismology, which is what we're talking about, I don't see how that can help. Local, yes, because local helioseismology from the ecliptic is basically, you can't go very high latitude because of foreshortening. And so if you really want to know the flows in the pole or something like that, you need to observe from the poles. But yeah, global, again, you're still observing the global mode, so it doesn't matter where you're observing them from.
Phil,
so having said that, of course, there's some mode physics that may be part of the systematics that having solar orbiter can help with.
Yeah, particularly if the active bands actually behave very differently from the the non.
Yeah, but just asking you, what is the consistency when you look from two different angles?
Yeah,
I've been looking a little bit at that lately, but it's solar orbiter doesn't have a lot of data.
10 days, it's not really much to do global helioseismology, is it? 10 days?
We have 8 hours at the moment.
Oh, okay.
Phil, do you have another question that you wanted to ask? I'm just trying to be sorry if I'm cutting into the conversation. I just want to make sure everyone gets to ask their questions before.
Yeah, I just wanted to point out that when MDI data is used, one needs to be very careful to not mix the orientations of SOHO, because we know that there's a difference when SOHO is upside down, that MDI is poorly calibrated and it influences almost everything. So that may be a big part of it.
But the only conclusion you make from that is wrong in both directions, right?
Well, yeah,
the instrument doesn't need to turn it upside down, so it's wrong the one way, it's probably wrong the other way, right?
Well, but from looking at the noise and looking at what happens to the magnetic field, we know that the upside down is worse than the right side up. So.
Yeah, but fundamentally, it still indicates an instrumental problem that you would have to worry about in the other configuration, right? Yes, it looks better, but there's nothing fundamental that made the design like that. It's just random what's up and down, pretty much.
Is there a
We didn't recalibrate when we turned it upside down.
That's
And we
right.
knew we had to calibrate it in the orientation that it was observing in. So we're trying to fix that now.
Lauren, it seemed like maybe your question was answered when Nick was talking, but did you want to follow up, or did you want to ask a more pointed question or anything?
I think so. So, I mean, just to clarify, it sounds like there is not a consensus whether like this geostrophic turbulence would drive the system towards solid body rotation or away from it, basically the frictional or anti-frictional point of view.
No, it's still inconclusive. Typical thing sort of happens, like Martin issued a piece of work, but then everyone said, well, those weren't great boundary conditions. And even his said showed sort of like latitudinal friction and radial anti-friction. So there's a bit of both. And if you throw a bit of magnetic field in there, everything changes. Yeah, there's work to be done there still, for sure.
Sushant had a question in the chat. Sushant, I don't know if you want to speak up and ask it, or me to read it for you. Sushant Mahajan.
Yeah, so my question basically was kind of connecting what we know or don't know about the tachocline to the solar magnetic cycle. What do we think causes the amplification of magnetic field? Is it the radial shear in rotation or the latitudinal shear? Because if it's the latitudinal shear that's dominant, then the presence or absence of a tachocline shouldn't make a lot of difference. But I wanted to ask what your thinking was.
Well, nobody knows. Is the simple answer to that one. Once again, you could say, you could look at mean field dynamo models, right, and see what they do. And then you can design a mean field dynamo model that works with either. But you can design mean field dynamo models that don't have any tachocline. That's the danger of mean field dynamo models, right? Is you're not terribly constrained, unfortunately. So yeah, it's a good question. I mean, and the answer is nobody knows really.
And you can do the same with 3D models. You can do models with have a tachocline and models that don't have a tachocline. But certainly with models that do have a tachocline, the radial shear is dominant.
Yeah, my feeling is it's most likely to be radial shear, right? Because then you can always use radial shear. You can create a sheet of magnetic field, and then it can have natural instabilities. Magnetic buoyancy instabilities have a natural scale, which is the thing that's going to give you a sensible scale for active regions. But this is essentially a hunch.
So I had a question that I think Lauren answered, but I'll raise just in case Nick or Gustavo or anybody else has other thoughts on it. My question is if the fossil field scenario is the true scenario, why do we have a solar cycle? Like what's the connection between that and the solar cycle?
Well, that's a completely different process, right? I mean, you can have a dynamo operating in the convection zone on the upper tachocline and a fossil field bouncing the spread of the tachocline. These are not incompatible things.
Okay.
I mean,
I think that's
most models don't have all of these dynamics. That's the problem. I mean, you're right to wonder. There hasn't been a model that incorporates all these things yet. And that's the thing, right? So you tend to see these things as either a dynamo model or a tachocline model, but it's not incompatible. These things can all happen at the same time.
Mm-hmm. Sarbani had a question. Again, Sarbani, I don't know if Lauren maybe answered your question, but if you want to.
Yeah, it was just that it was the graph Nick showed with the pure hydro and the MHD simulation, even though the colors were the same and the color scales had different extents. One was plus or minus 250 nanohertz, the other was plus or minus 25, if I remember correctly. And I just wondered, why is that? And I think Lauren said it's because magnetic fields are suppressing.
Yeah, it
differential
seems to
rotation?
be roughly equivalent to, like, if you have a convection zone only simulation, we also get the same thing. I think I also went to a very high Prandtl number there. It was like magnetic Prandtl number of 8, and then that seems to really suppress the differential rotation. I think it's a different sort of process than the one that's suppressing differential rotation in the radiative interior. But in that model, I've been kind of only focusing on the radiative interior because that's the most striking thing. I think it's still kind of an open question of like why the convection zone and convection zone only model. It definitely seems like across different platforms, different research groups, it really always seems to drastically diminish the differential rotation at some point.
Yeah, I just wanted to be sure that I'm reading the numbers correctly, and I am actually.
Yeah, there were 25 and 250.
Yeah, 25 and 250 because the color distribution was the same.
Yeah. So yeah.
Thanks.
And then I had one more question from, in the chat that so Nick, I liked your slide that had it kind of like spelled everything out with like the hydrodynamic and the magnetohydrodynamic and splitting things into slow, fast, all of that. If any given one of those is true, does that kind of nix any of the others in terms of like other stars? Could any one of these processes be true for a different star, but not necessarily in the sun? Like what does it mean? What are the implications if we determine that one of them is what's happening in the sun?
Well, I mean, I'm not even clear that it's going to be, just pick one. It seems it's entirely possible that it's going to be a combination of some of these things. And all these processes exist. It's just a matter of what's dominating, what's the dominant balance, right? Mm-hmm. As for other stars, it's a little hard to say because we have even less information on other stars to sort of constrain things, right? I mean, other stars either have tachoclines or they don't. If they have a tachyclines, once again, all these things might be possible. I don't think that we have enough information about some other star which is sufficiently different for us to be able to say, aha, from alpha whatever, therefore we can eliminate this one at this point in time. But it's an interesting line of thinking for sure. I don't have a better answer for you than that right now.
Actually, there is, Nick.
Oh, go ahead, Gustavo. That's why you're here.
because if you see all the proxies for magnetic field observed in different stars, then you have, for example, H alpha or X-rays, and then you have all these the two regimes: saturated regime for fast rotation and then a decline of the activity with rotation, for slower rotation. And it seems to happen that when the stars start to develop a tachocline, they mostly fall in the declining stage of the declining part of that diagram. Also, for M-dwarfs, there is a difference between the activity versus Rossby number depending on the mass. And these stars have a tachocline depending, there is a mass limit of 0.3 solar masses where the M-dwarfs start to develop tachocline, and there is a difference.
Sorry, Gustavo, do you really mean develop a tachocline or develop an interface between a convection zone and radiative zone?
There is an interface.
Yeah, because the stellar community always confuse the base of the convection zone with the tachocline, and they think it's the same thing.
Yeah, but there are. It's possible to measure, or there are a few works of measuring differential rotation, right? And
not really.
Especially for the fast rotating stars, and it's clear that the fast rotating do not have any differential rotation, and they are all of them in the saturated part of these diagrams. And then, as you say, it's very hard to say, but there are a few trends differentiating these stars that have radiative interior, to be more clear, than those that are fully convective. There are some difference in the activity versus rotation diagrams.
That might be an interesting standalone seminar to talk about stellar tachoclines.
Yeah, I mean, it's difficult to say exactly what is going on. I mean, we can talk about activity, but as we've already seen from simulations, you can have a dynamo cycle without any sort of tachocline whatsoever, just a convection zone dynamo. So it's hard to know how you relate this to what's going on in tachoclines, which is I guess, was the point that I was making. But
are there any other questions? We are well past our hour, but if anyone has any questions, then let's thank our speakers. And thank you so much for a really successful seminar. We had 50 attendees. So that's, I think that's a record.
big thanks to the rest of the team. Thanks, Sarbani. Thanks, Sylvain. Thanks, Gustavo. Thanks, Lauren, for monitoring the chat and answering the questions there.
Thank you. Thank you.
He's already on board. That's great.
Bye-bye.
Bye, guys.
Bye.